Hello everyone. In this video, we're going to discuss calculating probabilities using R. My name is Fred Rispoli, and I'm coming to you from Stony Brook University in New York. So R is a statistical programming language, and it's contained in RStudio. RStudio is a free and open source integrated development environment for R, as I said, a programming language for statistical computing and graphics. So in this video, we're going to go over functions provided in R to calculate probabilities for the following probability distributions. We'll take a look at three discrete distributions: the binomial, the Poisson, and the geometric, and three continuous distributions: the exponential, the normal, and the gamma distributions. So we start off with the binomial probabilities. Okay. In R, we could use the following code for calculating the binomial probabilities. We'll use B binom of X and P. So we could think of this as the probability mass function, or PMF, as I'll use. And this is used to calculate exact probabilities. When we want cumulative probabilities, we begin with P. So we have P binom X, comma, N, comma, P. So this is the cumulative distribution function, which you sometimes see abbreviated as the CDF. So just keep in mind that in R, the first letter is D for exact probabilities, and we use P for cumulative probabilities. And this is true for all the probability functions we're going to talk about in this video. As an example, let's suppose X is a random variable that's binomial. Here N is 12 and P, the probability of success, is 0.3. And suppose we want to calculate various probabilities. So I'm going to show you answers obtained two different ways. The first way would be using the binomial PMF formula, or perhaps a binomial table. So if we wanted the probability X is less than or equal to 7, okay, so I first note that this would be an instance of a cumulative probability. Okay, we want the probability where X is 1, 2, 3, 4, 5, 6, 7, all added up. That's indicated by this formula over here. So here we have the sum as X goes from 0 to 7, and this would be the PMF. And it turns out that this works out to 0.9905. So in R, the code would be P binom. Okay, so I'm using P for cumulative, binom. 7, that is my X value. 12, that is our value for N, and 0.3. And again, this works out to be 0.9905106. So this would be our output in R. Keeping with the same random variable, suppose we now want the probability X is equal to 7. So this is what I would call an exact probability. Just want the probability X is equal to 7. Okay, so if we just use this formula where X is 7, the PMF, we would get 0.0291. If we want to calculate this using R, we now use D binom 712.03. So it looks almost exactly the same as what we had above. The difference is just in the first letter, and this works out to 0.02911147. As a third example here, let's take a look at the probability X is greater than or equal to 7. So I sometimes call this a right tail probability. So the first thing we may do is try to express this using its complement, because When we do that, we convert the problem into a cumulative problem, right? So this probability would be equal to 1 minus the probability x is less than or equal to 6. Okay, so we could work this out using a PMF, and we get the answer 0.0386. Using R, we would have to write the code as 1 minus P binomial. Okay, so 1 minus, and then P because we're still using the cumulative, and then I have 6, 12, 0.3, and R we get 0.03860084. And finally, we have the variation where x is between two values. So if I wanted the probability x is greater than or equal to 4 and less than or equal to 7, here we're going to use the cumulative distribution function twice, right? So we would work this out. Probability x is less than or equal to 7 minus the probability x is less than or equal to 3. Remember, here we're interested in the values sort of where x is 4, 5, 6, and 7. So this gives us the probabilities for all values less than or equal to 7. We take away the probability for all values from 0 to 3. In R, we would use the CDF twice, both cumulative. So I have P binom 712.3 minus P binom 312.3. Okay, works out 0.49799949. Next, let's take a look at the Poisson distribution. So in R, we could use the following code for calculating the Poisson, which has just one parameter, right, lambda. And the code in R would look like D, P-O-I-S, D Pois. And then here we would have some x value and lambda. Lambda is the mean. So this would be the probability mass function for exact probabilities. And when we want it for the cumulative distribution, we simply start off with P. So here I get P, P-O-I-S, x comma lambda. And just one more time, the first letter D is for exact, and the first letter P is for cumulative. So some examples with the Poisson. Suppose a website gets 5,000 hits per minute on average. We want to use R to calculate the probability. Let's say it gets less than 4,900 hits in 1 minute. So less than 4,900. So this would be a case where we use the cumulative distribution. So I would have as my R code PPOIS 4899, right? I want less than 4,900, so I go down 1 to 4899, and then this is my average over the interval of interest. So I have 5,000 here, and we get 0.07726. If I want to take a look at a right-tailed probability, suppose we want the probability of getting more than 5,200 hits in 1 minute. So we have to solve this using the complement. The code looks like 1 minus P Poisson 5,200 comma 5,000. And you can see we get this small probability 0.002407183. Okay, and one more example here. If we wanted the probability of less than 10,300 hits in 2 minutes, okay, so now we have to adjust our average, right? We were given 5,000 hits per minute on average. So in 2 minutes, we would expect 10,000 hits per minute. So now I adjust this parameter here to 10,000. less than 10,300. So our X value would be 10,299. We have P Poisson, and this probability works out to 0.9985676. Okay, and one more discrete distribution, the geometric distribution. And here we'll just go right to an example. This one's a little bit easier. Suppose we know that a fair die is tossed until a certain number appears. Okay, well, for example, what's the probability that the first 6 appears at the 5th toss? Okay, so the experiment is we keep tossing a fair die, and we do that repeatedly until we get a 6. Okay, and so we want to calculate the probability the first 6 appears at the 5th toss. So here we could think of this as the geometric distribution. X is 5. P is the probability that you get a 6 on one toss, so that would be 1/6. So using the well-known PMF for the geometric distribution, probability X is equal to 5 would be 1/6 times 5/6 to the 4th power. We get 0.080. And we could also solve this using R. So here we use D because we have an exact probability. So D, geom, G-E-O-M. So 4, 1/6, and this would work out to be 0.080375551. So we match this. So that's how we could work with a geometric distribution. All right, now shifting gears slightly to continuous distributions, let's start by looking at the exponential distribution, right? We know the exponential is a continuous distribution, so for the most part, we only need the cumulative distribution function. We'll take a look at this. We don't need to use the exact, okay? But we're often interested in certain types of inverse problems, which you'll see we'll talk about as we go through these. So to calculate exponential probabilities with R, we would use P, EXP for the exponential, X, and then now we have 1 over lambda where the mean is lambda. Okay, so this is the CDF for the exponential. Now, sometimes we want to find certain percentiles, or I think of these as inverse problems. So we can do this with R, but now our first letter is Q. So if we use Q, EXP, P would be the percentile that we're interested in, or a certain probability, and then our parameter here is still 1 over lambda. And just keep in mind, this is what an exponential distribution looks like if we graph its probability density function, right? The exponential PDF. When we calculate these probabilities, we think in terms of this continuous function, and our probabilities represent certain areas under this curve. So for example, let's suppose the lifetime of a certain brand of light bulb has an exponential distribution with a mean of 800 hours. Find the probability that a randomly selected light bulb of this kind lasts, let's say A, 700 hours or less. So we can do this as P, EXP of 700. That would be sort of our X value. And we take 1 over 800, right? The mean here is lambda is 800, and this works out to be our probability, 0.583138. And it's nice to visualize these probabilities, so I've included a distribution plot from Minitab. So you could see here, this is a left side probability, and here we're going 0 to 700, and you see the probability displayed over here 0.5831. As a second example here with this same random variable, let's say we wanted the probability that the light bulb lasts between 700 and 900 hours. Okay, so here I want, the probability x is between 700 and 900. So the R code would be PEXP 900. This is my cumulative value, so this would give me the probability from, let's say, 0 to 900, and then we have to subtract off everything less than 700, and we would get 0.092200955. One more variation on this. Let's say we wanted the probability the light bulb lasts longer than 800 hours. So now that would be a right-tailed probability. So 800 being over here. So that would be the area, to the right of some value here, 800. So we convert that thinking in terms of the complement. And here we would have 1 minus the probability that x is less than or equal to 800. So we get 1 minus PEXP, use an x value of 800, and 1 over 800 over here. So we get 0.3678794. All right. Sticking with this same random variable, x gives you the life length of a light bulb. Okay, so again, suppose that the light bulb has an exponential distribution with mean of 800, but now we change the question up. Let's say we wanted the 95th percentile. Okay, so I wanted a certain value that I know that, the light bulb would last, that amount and that amount or less with the probability 0.95. So here we would use Q EXP of 0.95. That's our value for P, 1 over 800. So 2,396.586. So again, we would think of this that along the lines that 95% of the light bulbs last roughly 2,397 hours or less. So as a distribution plot from Minitab, here's what we get. 2397, and the probability that it's less than or equal to this is 0.95. Okay, so this also tells us, using the complement, that 5% of the time the light bulbs would last longer than 2,397 hours. All right, next let's take a look at the normal distribution. So to find these probabilities using R, we know that we have the normal distribution. It's continuous. For the normal, we need parameters mu, the mean, and sigma, the standard deviation. So in R, we would use P norm, x comma mu comma sigma. That's our CDF. And for the percentile inverse problems, again, we use Q norm. Here we would put in the percentile that we're interested in, and then we have the mean and the standard deviation. Here is a graph of the PDF for a normal, right? We get our well-known bell-shaped curve. So as an example, suppose x is a random variable that's normally distributed, mean 100, standard deviation 15. If we wanted the probability x is less than or equal to 94, so typically we may work this out by converting this to the standard normal distribution. We find the z-score, 95 minus 100 over 15. So the probability we want is equal to the probability z is less than or equal to negative 0.40. So now we could look this up in a normal distribution table. We should get 0.3446. To do the problem using R, we would use P norm, 94, 100, that's the mean, 15, the standard deviation. You could see we get this same answer. And we could provide a graph of this using a Minitab distribution plot. You could see this is a left side probability. 100 is the mean, so we're interested in the probability. X is less than or equal to 94. Minitab gives us 0.3446. Let's say we wanted a value of X that represents the 80th percentile. So here are two ways to get it. We could solve this. The 80th percentile we'd have to figure out gives us a z value of 0.84. We set this equal to x minus 100 over 15. We'd work this out and get 112.6. Using R, we would have the code Q norm, 0.80. Okay, this is the percentile that we're interested in. And then we have 100, 15. We get 112.6. An example of an inverse normal problem, okay, is suppose we have X has a mean 100, standard deviation 15. What value represents the 80th percentile? And here you see this same problem that we just did. All right, finally, we have probabilities for the gamma distribution. The gamma distribution is, again, a continuous distribution with parameters alpha and beta. To calculate these probabilities in R, we use P gamma. And the parameters here are X, alpha, and 1 over beta. To find a percentile, we would use Q gamma, P, alpha 1 over beta, and the mean for the gamma distribution is alpha times beta. So one example, if X is gamma with alpha equals 2 and beta equals 4, find the probability X is less than or equal to 3. So we would use P gamma, 3, 2, 1/4. Remember, this argument here is 1 over beta. We get the probability. And here you see a distribution plot. So we have this gamma distribution. Notice this PDF is definitely non-symmetric. And you can see we have X values down here. So the probability X less than 3, we get 0.1734. If I wanted the probability X is between 1 and 3, once again, we would have to use the CDF twice. So now I have P gamma 3, 2, 1/4, but minus P gamma 1, 2, 1/4, and we get 0.1468. For an inverse problem, if X is gamma with alpha equals 2, beta equals 4, let's say we wanted the 90th percentile. So here I would have Q gamma 0.90, 2, 0.14, right? The 90th percentile gives us this input right here, 0.90. This works out to be 15.5588. Okay, and here you see the distribution plot using R. So we know that the probability that X is less than 15.56 turns out to be 90%. So that's our 90th percentile. reached the end. Thank you for watching Probabilities with R.